6.2 Orbits. Satellites and space stations. A satellite is an object or body that revolves around another body that usually has much more mass than the satellite. For example, the planets are natural satellites revolving around the sun. Planetary moons, including the Earth's moon, are natural satellites too. Artificial satellites, on the other hand, are human-made objects that orbit the Earth or other bodies in the solar system. RADARSAT-1 and RADARSAT-2 are examples of artificial satellites. Another well-known example of artificial satellites is the network of 24 satellites that make up the Global Positioning System, GPS. By coordinating several signals at once, as shown, the system can locate an object on the Earth's surface to within 15 meters of its actual position. So the definition of a satellite is an object or body that revolves around another body due to gravitational attraction. And examples include planets and a planetary moon. An artificial satellite is an object that has been intentionally placed by humans into orbit around Earth or another body, referred to as artificial to distinguish from natural satellites such as the moon. And examples include RADARSAT-1, RADARSAT-2, Global Positioning System. Global Positioning System satellites, or GPS satellites, can determine the location of an object, in this case, a boat. The data from one satellite will show that the location is somewhere along the circumference of the circle. Two satellites consulted simultaneously will refine the location to one of the intersecting spots. But with three satellites consulted simultaneously, the intersection of the three circles will give the location of the boat within 15 meters of its actual position. The orbital motion of a satellite depends on both the centripetal force due to gravity and the satellite's orbital velocity. The equation for the satellite's orbital velocity is equal to the square root of gm divided by r. I want to introduce the concept of a geosynchronous orbit. The orbit around the Earth of an object with an orbital speed matching the rate of the Earth's rotation. So the period of such an orbit is exactly 1 Earth day. This satellite shown in this picture takes 24 hours to go around the Earth. It is also the same speed at which the Earth itself does one complete revolution, or rotation rather. The orbital period of the satellite and the rotation of the Earth have the exact same period. Therefore, the satellite remains over the same location in Earth as it travels around the Earth. This is really important, especially in telecommunications. This is how we communicate via cell phones. When our signal is sent from an antenna to a satellite that is geosynchronous above us, and then to another antenna, to the receiving person on the other end of the phone. Let's do an example, calculating the speed and orbital period of a satellite. The International Space Station, ISS, orbits the Earth at an altitude of about 350 kilometers above the Earth's surface. 350 kilometers is 3.50 times 10 to the power of 5 meters above the Earth's surface. So if we look at this distance, this would be the height of the International Space Station above the Earth's surface. The Earth itself has a radius. The radius of the Earth is 6.38 times 10 to the power of 6 meters. We want to determine the speed needed by the International Space Station to maintain its orbit. We know that speed is equal to g, the mass of the Earth, that is the force of attraction that is causing the centripetal acceleration, divided by the radius. Now the radius is going to be the radius of the Earth plus the height of the International Space Station above the surface. So we'll call this distance here r. And we can calculate that by adding these two together. If we punch them into our calculator, this radius is 7.7, I apologize, 6.73 times 10 to the power of 6 meters. So let's use this to find the orbital speed needed by the International Space Station to maintain its orbit. We have the gravitational constant, 6.67 times 10 to the power of negative 11. The mass of the Earth. Now this is a constant value. It wasn't given in the question, but that doesn't mean that you're not responsible for finding it. It's a constant value, can be found in any appendix. It's 5.98 times 10 to the power of 24 kilograms. Throughout your studies, you might actually even memorize this by accident just for using it so often. And we're going to put in our new value of the radius, 6.78 times 10 to the power of 6 meters. Now notice we don't have to square this radius. If we punch it into our calculator, we end up with 7.7 times 10 to the power of 3 meters per second. Perfect. In part B, they want us to determine the orbital period of the International Space Station in minutes. Period is equal to the time taken to travel one complete cycle. So we're looking at the distance traveled. In this case, it's equal to 2 pi r. That would be the circumference of the circle with the radius r, and divided by the speed. In this case, it's the orbital speed. So we have the distance traveled by the satellite and the orbital speed of the satellite. We can punch this into our calculator. That's 2 times pi times the radius we said was 6.73 times 10 to the power of 6 meters divided by the speed of 7.7 times 10 to the power of 3 meters per second. Now we want this in minutes. If we complete this calculation as it is, it will be given to us in seconds. So we can multiply it by 1 over 60. That's 1 minute per 60 seconds. Doing so will give us an orbital period of 92 minutes. Okay, sample problem number 2, we're going to calculate the speeds of planets around the sun. So we want to find the speed of Venus around the sun and the speed of the Earth around the sun. We're going to use our equations, G, and we're looking at the mass of the sun divided by the orbital radius of Venus. And we'll do the same for Earth. That's G times the mass of the sun divided by the orbital radius of the Earth. Let's plug in these values. 6.67 times 10 to the power of negative 11. I'm omitting the units just to simplify this, and also because I'm being lazy. Now, the mass of the sun is 1.99 times 10 to the power of 30 kilograms. In case you were ever wondering what the mass of the sun is, that's what it is, divided by the orbital radius of Venus, which is 1.08 times 10 to the power of 11 meters. If we punch this into our calculator, we end up with the orbital speed of Venus is 3.51 times 10 to the power of 4 meters per second. Let's do the same for Earth. I'm going to be lazy because I can. So the gravitational constant and the mass of the sun will remain the same. We're just going to substitute for the radius, the orbital radius of the Earth, which is 1.49 times 10 to the power of 11 meters. If we punch this in, we end up with an orbital speed for planet Earth of 2.98 times 10 to the power of 4 meters per second. Great. So we have the orbital speed of Venus and the orbital speed of the Earth, 3.51 times 10 to the power of 4 and 2.98 times 10 to the power of 4 meters per second, respectively. Try practice problems on 302 and review problems on page 303.